Jum Riab Sua. Well, that's the way we say hello in Cambodia. Hello, children. How are you people doing? I'm Saurabh Kumar Dutt, and I'm here to teach you people a little bit of physics. Now, children, this fascinating place that you get to see is actually Tonle Sap Lake in Cambodia. It is the largest freshwater lake in Southeast Asia. It is the most important waterway of Cambodia and is the home to 170 floating villages. It is here that you will have to have the mouth-watering sweet dish, which is Nam Chek Kachan, a Khmer layer cake, which I'm sure you will remember for life. And do remember to tell all the people of Cambodia that you get to meet Jum Riab Sua. In this note, children, we are going to start off this lecture on current electricity. Now, do remember that whenever we talk about electrical energy, it is the most useful form of energy because it is very easily interconvertible to other forms of energy like heat energy, light energy, mechanical energy, etc. Now, when we talk about electrical energy, obviously we require some electric current. Now, what is an electric current? So, if suppose there are some flow of charges, then it will be said to be an electric current. So here, children, we can see that the battery is one which has two terminals, and from the positive terminal is the current which is flowing in the direction of the negative terminal, which is the direction of the conventional current. And actually the electrons are flowing from the negative terminal to the positive terminal, which is the direction of the actual current or the electronic current. Now, when the current passes, this electrical bulb is getting lighted up. This is actually what electric current does. So one thing that you got to remember is whenever you talk about an electric current, it is actually the passage of some charges. Next, now, children, we talk about the next thing, that is we will now talk about charges, because just now I talked about charges. So what are charges? Now, children, charges can either be positive or negative. Remember, when we talk about charges, positive or negative doesn't give you the meaning as if it is something which is plus or minus. That means just like plus 10 or plus 15. It is just like a name. Like suppose we can have a name like Peter, we can have a name like Rohan, Rahman, or whatever, right? So when we talk about a charge to be positive or negative, remember that it is just a name. Now, what is a positive charge? Now, whenever, children, we talk about a positive charge, we should have some silk cloth like the one that we have here, and we should have a glass rod. Both of these being uncharged at the beginning. Now, when the silk cloth is rubbed over the glass rod, what happens is the silk cloth is one which has less of free electrons, and the glass rod has more of free electrons. These free electrons tend to pass away from the glass rod to the silk cloth. As such, the silk cloth becomes negatively charged, and the glass rod, losing electrons, becomes positively charged. For that matter, you always require remember that whenever we have charges which are moving away, right, it is actually the electrons which move, not the protons, because the protons are tightly bound within the nucleus with the neutrons by a force which is known as the nuclear force, right? So the silk cloth being rubbed with the glass rod, right, the excess electrons, they moved away from the glass rod to the silk cloth. As such, the glass rod now developed a deficiency of electrons, and thus it became positively charged. And the silk cloth, it received some electrons, it became negatively charged. Right now, children, after this we tend to have this observation that whenever there are charges which are of the type of charges which developed in the glass rod, they are said to be the positive charge. So this is the basic definition of a positive charge, that the charges which were developed in a glass rod after it was rubbed with silk, right, is known as the positive charge. So that is how we recognize a positive charge. Now, after the, children, we have the recognition of a negative charge. For that matter, we call in some cat. Rather, we talk about some cat skin. That means the hide of the cat after probably somehow the cat passed away and the hide was taken off and this experiment was performed. So let's say we have a ebonite rod, right? That is another type of a rod, right? And when the ebonite rod is rubbed with a cat skin, now do remember that both of these at the beginning are uncharged, right? And when the ebonite rod is rubbed with the cat skin, then what happens is the cat skin has some deficiency of rather the ebonite rod has some deficiency of electrons, right? And the cat skin has an excess of free electrons which are on the surface. So when the ebonite rod is rubbed with the cat skin, these extra electrons, they tend to move away from the cat skin to the ebonite rod, and as such the ebonite rod is made to be negatively charged and the cat skin becomes positively charged. So what did I say just now? That when we talk about the cat skin is one which has some extra free electrons. That means these free electrons are on the surface of the cat skin. Now when the ebonite rod is rubbed with the cat skin, then what happens is these extra electrons, they tend to move from the surface of the cat skin to the ebonite rod, and thus the ebonite rod becomes negatively charged and the cat skin, losing the electrons, developing a deficiency of electrons, develops a positive charge. And this type of charge which is there on the ebonite rod is negative. So these were two names, the positive charge and the negative charge, which were given to these two different type of charges. One which developed on the glass rod due to a deficiency of electrons, right, was the positive charge, and the charge which developed on an ebonite rod because of an excess of electrons is known as the negative charge. So this is how you can identify whether a charge is a positive charge or a negative charge, trying to develop a relation with the glass rod or with the ebonite rod just to identify them, right? For that matter, if say we have a device by means of which we can hang say a glass rod and we can hang a ebonite rod, not to hang them to kill them, right, but just to hang them by means of a weightless and an inextensible string, right? And both of these say they are charged as they normally are. That means a glass rod is positively charged and an ebonite rod is negatively charged. Then as opposite charges attract each other, so the glass rod will get attracted to the ebonite rod. Now if we keep a charged glass rod and a charged glass rod close to each other, again similarly hung, right, then both of these glass rods having positive charge, they will repel each other. Similarly, if there are two ebonite rods which are kept close by, hung again by an inextensible and a weightless string, then again as similar charges repel each other, so both of these ebonite rods, they will repel each other, right? So after this, children, now that you have understood what actually charges basically are, right, we will now talk about the next thing that you need to understand. That is, we will now be talking about the flow of charge, because actually the flow of these charges is actually what constitutes electric current. So let's say now that we have a charged rod here, right, and let's say we have an uncharged spare here, right? So both of these are metallic, right, and when we're going to hold them, we're going to hold them by insulated devices. That means those devices which have some insulation, that means thus the charges won't be flowing out either to a hand or to the earth, that is of this charged or say uncharged spare, right? So if there is some charge, right, on some equipment, there is some insulation which is provided, so that that insulation allows the charges to stay on that substance and the charges don't flow away, right? So let's say we have two these devices, one is a charged rod and another is an uncharged spare. Now when the charged rod is brought in contact with the uncharged spare, which is here, right? Then obviously the uncharged spare has an equal number of electrons and an equal number of protons. As such, it is uncharged. But when the charged rod is touched with the uncharged spare, then the same type of charge is going to develop in both of these conductors. As such, due to a deficiency of electrons which was there in this charged rod, right, the electrons which were in excess in this uncharged spare, they moved over from the spare to the rod, right, and as such there was a deficiency of electrons which was developed in both of these. I will just repeat this all over so that there is a better understanding. Initially, when we talked about this charged rod, it was positively charged. That means there was a deficiency of electrons. That means whenever it comes in contact with some such substance which has an excess of electrons, obviously those extra electrons are going to flow inside this positively charged conductor so that it becomes more close to being neutral, right? So as such, when this charged rod was touched with this uncharged conductor, then what happened was, as the uncharged conductor had an extra number of electrons in comparison to the deficiency of electrons which was there in this glass rod, in this normal metallic rod, right? So as such, what will happen is these extra electrons, they will flow from the charged spare to the the uncharged spare to the charged rod, right? And as some electrons have gone away, thus there also develops some deficiency of electrons here, and thus both of these become positively charged. Remember children, whenever we talk about the flow of such a type of charges, where one charged substance is put in contact with another uncharged substance, then the flow of these charges is infinitesimally small in time. That means all of this happens very, very, very fast. Did you all understand? So what did I mean to say here? That whenever there is one charged body which is put in contact with another uncharged body, or probably another charged body, then the transfer of charges happens in very, very, very little time, or in other words we can say infinitesimally small time, right? So this is actually how charges flow. Now we come to the next thing, that is we will now be talking about electric current, right? So remember children that whenever we talk about electric current, that is represented by I, right? So now in your copies you can write electric current, and when we talk about this electric current, we will represent it with either a small I, or in certain books even it is a capital I, right? But actually what you will get to study in higher classes, it actually is represented by small I. And as you're seeing that electric current is actually the amount of current which is passed, right, through a specific point, but this is also studied with respect to time. That means whenever you talk about the rate of flow of charge, you will talk about electric current, right? So this is the definition of electric current, that is the rate of flow of charge is electric current. Now when we talk about the rate of anything, that means we are wanting to study it with respect to time. So here children, if we talk about the charge to be capital Q, and if we divide it by the time, so this is what electric current is. Electric current is the rate of flow of charge, right? Now this charge can be small, this charge can be large. Now here children, we try and define what can be the smallest amount of charge, right? That is actually the charge which is had by an electron, right? One electron has the fundamental amount of charge, that is the smallest amount of charge which is possible, which is 1.6 into 10 raised to the power minus 19 coulombs, right? So this is the electronic charge, or in other words, it's the most fundamental amount of charge. And this principle that electron has the smallest amount of charge and the charge cannot get smaller than this is known as the principle of quantization of charge, right? What is this known as? This is known as the principle of quantization of charge. This principle tells you that the smallest amount of charge which is possible is the charge of an electron, that is 1.6 into 10 raised to the power minus 19 coulomb. Right? Now children, remember here that this capital C that we've written actually represents coulomb, which is in the name of a scientist. Right? So what is this? This is actually coulomb. So when we write the name of the scientist, it is with capital C. However, when we write the unit, it is with small c. And remember another thing, that whenever we do write a unit, never write a s at the end, even if it is more than one, right? So if we talk about 2 coulomb, it is not 2 coulombs, right? It is just written as 2 coulomb. That means a s is never written, right? For that matter, quickly you can try and understand that if we talk about 10 seconds, where will we put the second s? Because how we represent second is by small s. So we can't write another s by writing 10 ss, right? So by that you can easily understand that whenever we talk about a unit, it is always written as a plural, although it is always written as a singular, although it represents a plural, right? Okay. Now children, when we talked about the quantization, the principle of quantization of charge, you understood this, that the smallest amount of charge which can be possible is 1.6 into 10 raised to the power 9 minus 19 coulombs. So whenever we talk about any other charge, it is actually going to be a multiple of this charge, right? So if we talk about a charge, say, which is 10 times the charge of an electron, right, it will be the charge of one electron, which is 1.6 into 10 raised to the power minus 19, which is going to be multiplied by 10. So that will give you the charge of 10 electrons. Similarly, you can have a million electrons, and then the charge of the million electrons will be 10 raised to the power 6, which is going to be multiplied with 1.6 into 10 raised to the power minus 19 coulomb, right? Now after this children, next now we talk about electric current and its unit. For that matter, you always will remember that electric current is a fundamental unit, a fundamental physical quantity, and its unit will become the fundamental unit, right? I'm sure you all remember that when we talked about the fundamental physical quantities earlier, then we talked about the physical quantities like length, mass, time, right? Now we talk about electric current, and after that we talk about another physical quantity as luminous intensity. We talk about amount of substance, we talk about temperature. All of these are fundamental physical quantities. There are 2 more fundamental physical quantities. One is plane angle and the second is solid angle, right? Then their units become the fundamental units. Like I talked about mass here, right? So when we talk about mass here, it's a fundamental physical quantity and its unit is kg, which is its SI unit, that is Systems International D units, right? Unit. Okay, next we talk about length and its unit is meter. After this we talk about time and its unit is second. After that, next we talk about electric current, as we just did, right? And the unit of electric current, children, is ampere. Again, it is in the name of a scientist. The name of the scientist, who was a French physicist, was Andre Marie Ampere, right? In his name, this unit of electric current has been given to you, that is, it is capital A. Now children, if we talk about the next physical quantity, the next physical quantity is luminous intensity. So when we talk about luminous intensity, its unit, children, is candela, right? So this is the unit of luminous intensity, and after this we have amount of substance, and its unit is mole. right? After this, children, next now we have another physical quantity by the name of temperature. Right, and its unit is Kelvin. Again, this is in the name of a scientist, right, and thus it will be written with capital K. Okay, so these are the normal physical quantities, which are the fundamental physical quantities, and their units are the fundamental units. Okay, so here, children, I will write that these are the fundamental physical quantities. Okay, and obviously their units will become what? Their units will become the fundamental units. Now, why is it that we talk about the units of these physical quantities to be the fundamental units? That means these units actually cannot be broken up into further smaller units. For that matter, I will quickly give you an example. Let's say we talk about 1 Newton. We know that 1 Newton is equal to 1 kg meter per second square, right? And here, as such, you get to see that this 1 Newton can be broken up into 4 units of 4 physical quantities, and thus it has been broken up into 4 parts. But if we look up trying to break up kg, it cannot be broken up, that is, it is just 1. And similarly, if you talk about meter, meter is also just 1. As such, it cannot be broken. And this is how, when we talk about each of these different physical quantities, none of these physical quantities can be broken up into further smaller physical quantities, and as such their units will be said to be fundamental units. Now, when we talk about the units of such type of physical quantities, like we talked about 1 Newton, similarly we can even talk about, say, 1 joule, right? And 1 joule is 1 kg meter square per second square. Here, what we've been able to do is we can now break this up into 1, 2, 3, 4, 5. That is, one will be kg, another will be meter, another will be meter, another will be second, and lastly we will have another second, which will give you all the different fundamental units. So such type of units, children, are known as derived units. What are these? They are known as derived units, because these have been derived from the fundamental units, and that's why they are known as derived units. Now, like I told you, there are 2 more supplementary physical quantities. So next now we'll be talking about those. That is, the word supplementary actually means helpful. So that's why these 2 units are helpful in talking about the units of all of physics. So we have these as supplementary fundamental physical quantities, which is an abbreviation that I've written. F stands for fundamental, P stands for physical, and Q stands for quantities, something that I've written above. And here, children, we'll be talking about their units. So first I said was planar angle, right? And its unit is radian, right? Then, children, next is solid angle, and its unit is steradian, right? These are things that you will get to study in probably class 11, or might be that you already studied, right? And this is how I give you an idea that when we talk about this electric current, it is a fundamental physical quantity, and its unit, ampere, is the fundamental unit in the list of all the fundamental physical quantities and fundamental units. Now, when we talk about electric current, you've just seen here that electric current is actually what? Electric current is the ratio of charge to time. So it is not that electric current's unit is being written in terms of the unit of charge and time, right? But actually the unit of charge is going to be written in the form of the unit of electric current and time. For that matter, if you talk about the unit of charge, it is 1 coulomb, right? And thus here, children, what we can do is we can write that Q will become equal to I, which is going to be multiplied with T, right? And as such, if you talk about the unit of charge which is 1 coulomb, 1 coulomb will be equal to 1 ampere second, right? That is, coulomb is a derived unit and ampere is a fundamental unit, right? So electric current is written to be the ratio of charge to time. The unit of charge is coulomb, right? And it's a derived unit which can be written in terms of two units: the unit of electric current, which is ampere, and the unit of time, which is second. Now after this, children, comes the next thing, that is the direction factor that we talk about electric current. So whenever we talk about an electric current, we talk about it to be one that is having a direction also and not having a direction also, right? So I'll give you quickly a split of a second in which you try and think, why is it that electric current has a direction also and doesn't have a direction also? I'll give you 10 seconds to quickly reflect. Yes, do think with your own self. Don't try and look up in your computer or probably in your mobile. When you think with your own self, then you increase your intelligence. Okay. Now actually what happens, children, is when we talk about electric current, remember I showed you a circuit just now, right? And here we talked about electric current to be one such which moves from the positive terminal to the negative terminal, as is the direction of the conventional current. And the direction of the electronic current is from the negative direction, from the negative terminal to the positive terminal, right? This is the actual flow of electrons, right? So this is how you can say that the direction of electric current is going to be, the conventional direction will be from positive to negative. And when we talk about the direction which is from the negative terminal to the positive terminal, it will be the direction of the electronic current. So I will write it here also, that when we talk about this direction, this is actually the direction of the conventional current's direction. A conventional word means what? Something which is coming age old. Initially there was not this reasoning that actually the current moves from the negative terminal to the positive terminal in the external circuit, as the electrons, they move in the external circuit. So the actual direction of the current is the direction of the electronic current, that is opposite to the direction of the conventional current, right? And when we talk about the direction of current from the negative terminal to the positive terminal, it will be considered to be the direction of the electronic current, right? Or we also talk about it to be the actual current's direction, right? So this is the direction in which actually the electrons move, and this is the actual direction of electric current, right? So in a way you can say that the direction of the electric current is two. One is the direction which is being normally considered to be true, that is the direction which is coming age old, which was without any reason, right? And the other, which is the direction of the electronic current. Now there's another reasoning which tells you that if you talk about the direction of the electric current, it is actually no direction. That is because when we talk about, say, a wire, let's now talk about trying to draw a wire here. So let's say we talk about drawing a wire here, right? So let's say we draw here a wire which, say, is in this direction. Just a second. When we talk about the direction of the wire, let's say the direction of the wire, say, is something like this, and let's say the current, that is the electrons, are flowing in it in this direction, right? So this is the direction of the current then. And as you know that if we talk about a wire which contains some flowing electrons, as you know that it is not hard, it is something which is easily turnable, right? For that matter, let's consider your physics laboratory, where you can be having a circuit where there can be a battery which is connected to, say, some resistance box. ammeter, voltmeter, some other resistors, some electric bulb, a fan, etc. Now obviously there are these insulated wires with the help of which you attach the terminals of the battery to the different electrical devices, right? And there you can find that the direction of the current is probably from one direction to another current. Now tell me, is it not possible that you change the direction of this wire, say in this direction? Yes or no, you tell me, right? So if say you want, you can turn the direction of this wire, say from here onwards in the downward direction like this. Let's say this point be say some point A, this be say some point B, and this say be some point C. Now from the point B, you can turn the direction of the wire in this direction, in the downward direction, right? If you want, you can even overturn it in the opposite direction. Let's say if you want to change this, let's say you want to change this in this direction, right? So here what will happen is this will be the end A, this will be the end B, and this will be the end C. Now earlier, if you were talking about the direction of the current, it was going in this direction. Now that you changed it, now it is going in which direction? It is going in the other direction. That means it is going in the right hand side. Earlier it was going in the downward direction, so the direction of the current is actually changing, right, in accordance with either you turning the wire or probably the wire getting somehow the other turn, because as you know that they are not hard devices, right? When you move some part of the circuit, then obviously the direction of the wire, even if it changes a little, you will say that the direction of the current has changed. But actually there is no impact in the different physical quantities which are there as part of the circuit. That means due to this change of direction, the voltage or the resistance or some other factors in electricity don't change. And that is the reason why the direction of the electric current is something which is not considered to be one that requires some attention. When the direction of a physical quantity requires some direction, that means if the direction changes, the impact on other physical quantities changes, then we say that the direction is important, and then we talk about that physical quantity to be a vector quantity, right? For that matter, if we talk about force, we know that force is a vector quantity. A little direction changes, then the impact on other physical quantities changes. If we talk about velocity, we know that velocity is a vector quantity, because if say there is a car which is moving towards the north, if it changes its direction perpendicular to itself, now it will not be moving towards the north, it will be moving towards the east, right? So when the direction changes, the physical quantity also changes. But with electric current, this is not happening. That is, if the direction of the wire is changed or is twisted a little, then the impact on the other physical quantities doesn't change. And that is the reason why electricity's physical quantity, electric current, is said to be one which is a scalar quantity and is not considered to be a vector quantity. Did you all understand? So this is why I said to you people in a dubious way that tell me whether electric current is one which has a direction or not. I said that it has a direction, it also doesn't have a direction. So I explained to you that when we talk about that electric current is passing in a circuit, so either it will be moving in the clockwise direction, if suppose we talk about the direction of flow from positive terminal to negative terminal, and if you talk about in the same circuit, the direction of flow of current will be in the opposite direction if we talk about the electronic current. So this is where we talk about it to be having a direction, right? But this direction can be changed a little if the wires are turned or twisted a little, and that doesn't impact the other physical quantities numerical value. And that is the reason why you say that it is a scalar quantity and it is not a vector quantity. That means electric current doesn't have an actual direction. So is all of this clear? For sure. Sanjana, Mahi, everybody clear? Sure? Very good. So children, that is all that I have for you people in this lecture. Now I'll meet you people again and we'll study more, right? Bye for now, and make sure you practice all of this, make notes and learn all this up. Bye, children.